Hi everyone. In this video we are going to cover section 4.4, the mean value theorem. We'll get to that a little bit later in the video. We'll start out with what is called Rolle's theorem. Rolle's theorem is a nice lead up to the mean value theorem. So here's the theorem here. You can pause it and read it for yourself. I'll highlight the important aspects of the theorem. We have to have a continuous function over some closed interval that is also differentiable over that interval as well. So the closed interval AB, it has to be continuous. The open interval AB, it has to be differentiable, meaning the derivative has to exist. And also, the other condition that is really important to Rolle's theorem is that f of A is equal to f of B. Okay, so if that is the case, then there exists some point inside of that interval, we'll call it C, such that f prime of C, such that the derivative, the slope at that point, is 0. So that's what Rolle's theorem says. Now let's get kind of a visual representation of what that means. All right, so I am going to draw myself some axes here, and like that, there we go. Here I have my x and y axes. Okay, and I'm actually going to duplicate that so I can draw another picture in just a minute. There we go, put that over there. Okay, so there's my axes. And if I have a function and I have an A here, and we'll put B right there, if f of A equals f of B, and I play connect the dots, there is somewhere inside of that interval C, such that the derivative at that point, the tangent line at that point, despite my little bit lackluster drawing, the derivative at that point is 0. Okay, there's no way to play connect the dots without having a horizontal tangent line. Okay, and what I mean by that is there is no way to go from this point to that point, and the f of A equals f of B. That means their y coordinates are the same. That's what that means. So there's no way to go from one point to the other without having a horizontal tangent line. So there's a horizontal tangent line. Hey, I could have every point between A and B have a horizontal tangent line. If I play connect the dots with a horizontal line, the slope is always 0 if I have a horizontal line. Okay, there's a couple other examples in OpenStax, a couple other pictures, but that's what the theorem is. And it's important that the derivative is, the function is differentiable over that interval also. We can draw it so that there's no point f prime where f prime of C is 0, but it'd be a case where the derivative doesn't exist at that point, and so then Rolle's theorem wouldn't qualify. All right, enough setup. Let's look at an example scrolling down. Okay, so it says for each of the following functions, verify that the function satisfies the criteria stated in Rolle's theorem and find all values of C where the derivative is equal to 0. All right, so first of all, the verify. That is a polynomial function, so it is continuous. Polynomial, so continuous. And differentiable. Differentiable. Those are important. It has to be continuous. Derivative has to exist in order for Rolle's theorem to apply. And then the extra condition, if I test each endpoint of the interval, f of -2 is -2 squared plus 2 times -2. -2 squared is 4 minus 4 is 0. That has to be equal to f of 0. 0 squared plus 2 times 0, also equal to 0. Hey, there we go. So has to be continuous, has to be differentiable, and the function value at the endpoints has to be equal to each other. Okay. Actually, I'm going to add on to my phrase at the top, polynomial, so continuous and differentiable for all real numbers. There we go. That's important. For all real numbers, and specifically over the given interval. Okay, so then the rest of the work of the problem is to take the derivative, f prime of x is equal to 2x plus 2, set that equal to 0, subtract and divide, and you get that x is equal to -1. So we have that our C is -1. Okay, that's how that one works. And let's scroll down a little bit, and we can do B. Draw a little line separating them. Part B. Again, this is a polynomial, so I could just grab that all again. This is a polynomial, so we are continuous and differentiable for all real numbers. There it is again. All right. Again, that's important. That has to be true, or else Rolle's theorem wouldn't apply. We'll test our endpoints. F of -2, -2 cubed minus 4 times -2. -2 cubed is -8 plus 8 is 0. F of +2, 2 cubed minus 4 times +2. 2 cubed is +8 minus 8, also 0. Now, it's just coincidence that in A and B we get 0 for when we evaluate the endpoints. That's not always going to happen. It's just coincidence in this problem. Okay, but because we got the same y coordinate, that guarantees that we're going to find a point where the derivative is equal to 0. So this would be 3x squared minus 4 is my derivative. And when I set that equal to 0, add the 4, divide the 3, x squared is equal to 4/3. So then we take the square root. X is equal to, this would technically be plus or minus 2 over radical 3, or I could rationalize and write it as 2 radical 3 over 3. But that's what we get as solutions. There we go, to show my square root sign that I'm doing there. Square root of 4 is 2, and radical 3 in the denominator. All right, so we get 2 points in this one. Now, one thing that I didn't mention in A, and I'm going to mention now, is that C, and this was important, I shouldn't have left it off, but I did on accident, that C is inside of the given interval. It is between -2 and 0. That was guaranteed that we would find a point, not just that it exists, but it's between -2 and 0. Okay, so what is this 2 over the square root of 3 in decimal form? And then do those both fall between, in this case, -2 and +2? So if you check in your calculators, 2 divided by the square root of 3 is approximately 1.15. Fit that in there. So positive 1.15 and negative 1.15, those are certainly inside of the interval from -2 to +2. So in part B, our C points are this plus and minus 2 over radical 3. Again, you could also write that as 2 times the square root of 3 over 3. But I'm fine with the radical in the denominator. You don't have to worry about rationalizing it. Now we get to the mean value theorem, and instead of giving you the theorem first and then drawing a picture, I'm going to draw a picture first. I think that will help this to kind of visually make sense what is going on here. So the mean value theorem, here's my x and y axes. It says that if I have some function, then I'm going to draw my function like that. This is y equals f of x, that is continuous and differentiable over some interval, and I can pick my interval to be anywhere. So it removes the condition that f of a has to equal f of b. Okay, so anywhere along my function, I'm going to pick this point right here and call it a, and I'm going to pick that point right there, and I'll call that, it's a little bit off the line there, but that's okay. I'll call that point b. Okay, then the y coordinates are f of a and f of b. But the mean value theorem says that if I find the slope of the line connecting those 2 points, so the m would equal f of b, I'll write it off to the side here, m is equal to f of b minus f of a minus, over b minus a. So the slope of the line connecting those 2 points, there is some point inside of that region, inside of that interval from a to b, that would have the exact same tangent line. And I'm going to put it right there because that's where it looks like it would approximately be. Okay, there is some point C in there that has the exact same tangent line. So I could find a point C such that f prime of C, the slope at that point, is equal to the slope of the line connecting the 2 points. So then I'll scroll down a bit, and here we have the formal statement of the mean value theorem. If I have a function that is continuous over the closed interval from a to b, differentiable over the open interval, so the same setup as Rolle's theorem, but it removes the condition that f of b has to equal f of a. Then there exists at least one point c, can find one or more than one, inside of that interval, such that the derivative at c is the slope of the tangent line connecting a and b. So the slope is equal to the slope. The slope at the point is equal to the slope between the 2 points. All right, that is the mean value theorem. So now let's look at an example or two. All right, here's our first example, and we're going to start out by verifying that the mean value theorem applies. We're given a function f of x equals radical x. Our closed interval is 0 to 9, and we need to show that f satisfies the hypotheses for the mean value theorem. And the reason that this one's a little bit different than the last two is because this is a square root function, not a polynomial function. So this is not defined for all x. But the function f of x, oops, how am I going to write this? F of x is defined and continuous on the closed interval from 0 to 9, and it is differentiable on the open interval from 0 to 9. The derivative technically does not exist at 0. It does not exist at 0 because there's no limit from the left of 0. But the open intervals, once you get a little bit above 0, the derivative does exist after that. Okay, and it is continuous. We can take the square root of any number between 0 and 9, including 0 and 9. So the mean value theorem here applies. So the next step is to find one part of the mean value theorem, and typically when I do these, I will start with the f of b minus f of a over b minus a, the non-calculus slope step. All right, that is f of 9 minus f of 0 divided by 9 minus 0. The square root of 9 is 3. Everything else is hopefully pretty straightforward. This simplifies to 3 over 9, or 1/3. So the slope of the line connecting the endpoints, the secant line connecting the endpoints, is 1/3. And the mean value theorem says that there's some other point, some c, between 0 and 9 that has that exact same slope. So step 2, we're going to take our derivative, f prime of x, and if my function is radical x, the derivative is 1 over 2 times the square root of x. And then I'm going to call it step 3. It's kind of the step where we'll set them equal to each other. And since mean value theorem says that it is this point c inside of the interval, I'm going to change my x to a c. 1 over 2 times the square root of c is equal to 1/3. Okay, and to solve this, let's see, I can cross multiply, cancel out the denominators, lots of different ways to show this, but then I'm going to write 2 radical c is equal to 3, divide both sides by 2, radical c is equal to 3/2, and then, big fancy step, I'm going to square both sides of that equation, and my c in this case is 9/4, 9 over 4, which is, what is that, 2 1/4, which is certainly between the interval from 0 to 9. 9/4 is in there. And if I scroll down, we can see visually what we just found. Okay, so this dotted line at the bottom here, this is the slope of the secant line connecting the endpoints. Here's the tangent line at 9/4, and the calculus that we just did above is saying that those two slopes are the exact same. And in our next example, we're going to be looking more of an application type question. In this one, we have a rock that is dropped from a height of 100 feet, and we're looking t seconds into the future. And it's given by, the height of that rock is given by that function, negative 16t squared plus 100. And we've got a few different parts to this problem that we have to go through. Part A wants us to determine how long it takes before the rock hits the ground. Okay, so we want the height of the rock to be 0. It hits the ground when s of t is equal to 0. So we'll set our negative 6, that's an arrow there, doesn't quite look like an arrow. We'll set our negative 16t squared plus 100 equal to 0. That says that 16t squared is equal to 100. We divide both sides by 16, and then take the square root to find that t is equal to plus or minus 5 halves. So I did 100 divided by 16 and then took the square root. And then since we're dealing with, time and an actual rock dropping, we're just going to take the positive solution, the positive t value there. So that part A really gives us our interval on which to apply the mean value theorem. The rock is dropped at 0 seconds. It hits the ground at 2.5 seconds. That's what 5 halves is. Okay, so that's how we are going to apply the mean value theorem, or the interval on which we apply the mean value theorem. So we'll do that in part B, where we find, well, the slope between 0 and 2.5 seconds, that is just the average velocity of this rock over the trip downward. So we go v sub a v g is equal to, this is s of 5 halves, plug that into the position function, minus s of 0 divided by 5 halves minus 0. Substitute 5 halves into the function, you get 0. You should. That's what we found out in step 1. Minus s of 0 is 100. And then in the denominator, we have 5 halves. So we get that the average velocity, when you type that into your calculator, is negative 40 feet per second. Negative 40 feet per second. Okay. Now, part C, find the time t guaranteed by the mean value theorem. So for part C, we need to take our derivative and then set it equal to what we got in part B. The derivative is negative 32t. And then we set that derivative, and I'm going to use c again. Negative 32c is equal to the answer we got in the previous step, part B, equals negative 40. Negative 32c equals negative 40. Divide both sides by negative 32. And when you simplify that fraction, divide numerator and denominator by negative 8, you get that c is equal to 5/4, or 1.25 seconds. Okay, so the speed of the rock as it's falling is at 1.25 seconds. The instantaneous velocity is equal to the average velocity over the whole trip down. And we can see what that looks like on this graph. So this dotted line is the average velocity over the whole trip being thrown downward. And then here at 1.25 seconds, we have that the instantaneous velocity, the speed at that moment in time, is equal to the average speed over the whole trip. All right, so that is the end of section 4.4. Go work on some of the homework questions. Let me know if you're struggling. I can provide a couple of other examples, or we can meet and see if I can help you figure out what's going on. Just let me know what type of supports you need. Thank you very much for listening. Have a wonderful day.